Hey guys! In this video we will continue developing our AZDO-based renderer. AZDO stands for Approaching Zero Driver Overhead, and if you haven't watched my previous video, make sure to do so. It explains how to implement indirect rendering, which can potentially reduce the number of draw calls in a single frame to 1. At the point where we left off, we were able to use GL multi-draw elements indirect and get a transformation matrix for each submesh in the scene from a dedicated SSBO. The problem is that we lost the ability to switch textures between submeshes because this requires binding the textures before each submesh, and the loop over the submeshes has been offloaded from the CPU to the GPU. The solution is to use Bindless Textures, which is a feature that allows us to bypass the texture binding mechanism and connect the shader to a texture directly via a 64-bit texture handler. This feature is available as an extension and is not part of the core OpenGL specification, so it may not be available on every GPU. However, it was introduced already in 2013, and according to Copilot, all NVIDIA GPUs starting with the GTX 600 series and all AMD GPUs starting with the HD 7000 series support Bindless Textures, so I hope that you'll be able to use it. The Bindless Textures API is very simple and mainly includes two functions. First of all, we have GL getTextureHandle ARB. This function takes a regular texture handle, which was created using GL createTextures, and converts it to a 64-bit identifier. I will use the terms handle and identifier to distinguish between the old and new handles, respectively. A texture handle must be bound to a texture unit, while the texture identifier can be loaded into the GPU using an SSBO. But before we do that, we need to make the texture resident in GPU memory, which is something the texture binding does, sort of. So the next API call is GL make texture handle resident ARB, which takes a texture identifier and places it in GPU memory. If you have lots and lots of textures, you may run out of GPU memory, and you will need to implement a memory manager to cope with low and mid-range GPUs. Therefore, we also have GL make texture handle non-resident ARB, which tells the driver to remove the texture from GPU memory. We won't be using this function in this video, but this is something to keep in mind if you're targeting a wide range of GPUs. Okay, before we jump into the implementation, I'd like to say a big thank you to OK Matija, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev, or by joining the YouTube channel as a member. Okay, so I'm going to show you two examples. The first one is a simple sandbox, just to see the new API in action. This is a flipbook animation that switches between textures entirely on the GPU. The second example is more complex and involves adding Bindless Texture support to the indirect renderer that we saw in the previous video. Hopefully, it will make it easier for you to integrate it into your own implementation. This is the first example, the flipbook animation, and the idea is basically to animate a set of images from the 3D graphics rendering cookbook. Okay, so if you check out the code that comes from the book, from its GitHub page, and go to Depths and Source, then you have 3 folders with the explosion prefix, and each folder includes 100 images of the TGA format. Unfortunately, Windows doesn't know how to show the thumbnails, but you can probably install some Paint app which is able to view them. Now let's go to our code. As I said, this is a simple sandbox application which derives from some base class that provides basic infrastructure for initializing OpenGL, the camera and stuff like that, the window. And the main thing that the application initializes are the textures. And this function contains a couple of loops. Okay, so the first one goes over the number of directories, which is 3, and then the number of files in a directory, which is 100. And using snprintf, we construct the full file name of the current file. Very simple, we have the full path here, and we use the running indices to generate the file names. And once the file name has been constructed, we set it into a vector called texture file names. Okay, this guy is a vector of strings, and the number of elements is the number of directories times the number of files in a directory. So we now have a vector or an array of all the file names that we want to animate. And now the second loop, which simply goes over the number of files, loads the textures one by one. Okay, so textures is a vector of the texture class, which I've used many times before. The size of the vector is the same as this guy, and the textures are initialized to be texture 2D. So if we go to the load function, we use stbimage to actually load the image file. And if the version of OpenGL is more than 4.5, then we use direct state access or DSA to load the image. Otherwise, we use the non-DSA path. And what I did here is to implement bindless textures only on the modern version. Okay, so I'm kind of assuming that if the version is less than 4.5, then bindless textures are probably non-existent here. This may not always be the case, but I think it's good enough for this tutorial. So if we go to this function, what we have here is basically a standard initialization of an OpenGL texture using GL create textures and then texture storage 2D, texture subimage 2D, and we saw all that in the direct state access tutorial. But at the end of the function, after setting the parameters, we have a couple of calls to the new functions. Okay, so first of all, we call GL get texture handle ARB on the handle of the texture object. And this returns the bindless identifier, which is a new attribute of the GL unsigned int 64-bit. So now the class object contains both the texture handle and the identifier. And then we use the identifier to call GL make texture handle resident ARB, okay, using the bindless handle. Okay, so for a more generic implementation, you will probably need to check for the existence of the extension, and then based on that, enable or disable the logic path of bindless textures. But for simplicity, I will assume here that bindless textures exist, at least for OpenGL 4.5 or more. So going back to the application, the loop will initialize all the texture objects using the corresponding file name. And then for each texture, we extract the bindless handle. This is simply a getter of the identifier and set it into the third vector of the texture handles. Okay, so we have another vector here, this time of a 64-bit unsigned integer to match the identifiers. And the reason why we need a clean vector with only the identifiers is because we're going to load that into the SSBO. Okay, we cannot simply load the data from the textures vector because this class may include more stuff. For example, it includes the handle of the texture, and we don't need that. We just need the identifiers. Okay, so we get the identifier for the current texture and set it into the corresponding location in this vector. And now we create a buffers handle, and we use GL named buffer storage to load this vector into the buffer. Okay, so this is basically our SSBO. As you can see, the handle of the buffer, the size in bytes of the identifier vector, pointer to the start of the vector, and we don't need any hints. So now our SSBO is ready with all the texture identifiers, the 64-bit texture identifiers. From here, let's go to the main render loop. And what we're doing here is to call GL bind buffer base on the GL shader storage buffer target, which basically indicates that this is an SSBO. And we bind the texture buffer to the first binding point. As you will see in a minute, we have a corresponding binding point in the fragment shader. And since this is a simple example with a single SSBO, I'm simply using 0 here. When I have more binding point, as you shall see in the second example, then I use an enumeration of the binding points. Next, we call GL draw arrays to render a simple quad. Okay, 6 vertices for a full screen quad. But before we do that, because this is a flipbook animation, in each frame we want to switch a texture. So we go to the bindless texture technique, which is a special technique that I created for this tutorial. And we set the current texture index. And texture index is a simple static integer, basically a running index. As you can see, after the call to GL draw arrays, we increment the index, and when it reaches the number of files, we reset it back to 0. Okay, so the bindless texture technique makes use of two shaders. It uses the quad vertex shader to render the full screen quad. This shader comes from the common shaders directory, and it's very simple, you can review it offline. The bindless texture fragment shader comes from this project here, so let's take a look. The version of the fragment shader is set to 4.6 core, and you may be able to run this with previous versions, but I haven't checked. What we absolutely do need is the bindless texture extension. So we specify it like that, okay? Hash extension, the name of the extension, and then :require. So this will fail compilation if the driver doesn't support it. As you can see, we have a uniform integer for the current texture index. So this variable is updated by the application when we call setTextureIndex. The value simply goes directly into this uniform. Next, we have the definition of the SSBO. Okay, so we use the layout specifier to tell the system that this is on binding point 0, same as the application side. STD430 is also required so that the application and the shader can communicate the data in the correct format. Okay, defines stuff such as alignment issues that can ruin the transfer of data. This is a read-only buffer, and the name of the variable is SSBO. Not sure why it is SSBO3, I probably copied it from another tutorial. We don't need this one, and we can get rid of that. The vertex shader passes in the texture coordinates, and we use these coordinates to sample the color. But to call texture, we need a sampler 2D, and we get the sampler from the SSBO. Okay, going back to our SSBO, it contains an array of sampler 2Ds. You don't need to define the number of elements in the array, which makes this very convenient, so we can use the same shader code for a different number of elements. The size of the sampler 2D is 64 bits, so this matches perfectly the vector that we have loaded into the SSBO. So we use the texture index to access the array of sampler 2Ds in the SSBO. We extract the current sampler, and we use it to sample the color. Okay, so in this example, we have 300 textures that haven't been bound into the texture units. We simply made them resident in GPU memory, and we access them in the shader using an SSBO. So now let's run this. I have 3 different explosions here. 1, 2, and 3, and then it goes back to the beginning again. Okay, now let's see the second example, which is the integration of bindless textures into the renderer that we saw in the previous video. Now, most of the changes are in the new class that we saw in that video called indirect render. So I'm simply comparing it with the previous version on the left-hand side. Let's start with the private attributes and then continue to the functions. So first of all, as you remember, we have this vector of meshes or submeshes, and for each mesh, we maintain a transformation matrix. This transformation is pulled in the vertex shader, and we use it to calculate the WVP matrix for the current mesh because we can do that using uniforms, as we usually do. We now have a new attribute here called material index, which is an index into a vector of materials maintained by the core model class. Okay, let's see how this works. In the core model class, we have a vector called meshes of the basic mesh entry structure. This structure contains a material index, which basically points us into another vector of materials. Okay, and then the material, which is actually a class, contains 3 color vectors: ambient, diffuse, and specular. These guys are loaded by the SIMP library from the asset file. In addition, we have 3 pointers to a texture object: diffuse, normal, and specular exponent. Okay, a vector of meshes and a vector of materials. So we will need to load most of this vector into SSBOs and access the corresponding material for each mesh. So basically, a copy of this material index is stored in this private vector in the indirect render class. In addition, I have 3 new handles of SSBOs. to store the colors, the handles of the diffuse maps, and the normal maps. I actually tried to put all this information into a single SSBO, but I had some issues which I will show you later on. So remember that we already have two SSBOs here, one to hold the draw commands for the GL multi-draw elements indirect API, and one to hold the per object data, which now also includes the material index. So the SSBOs are basically OpenGL handles, but the information itself is stored in three vectors: the colors, the diffuse maps, and the normal maps. So the colors is a vector of the material color indirect, which is a simplification of the original material class. This just includes the three colors, okay, ambient, diffuse, and specular. The other two vectors maintain the 64-bit texture identifiers, which are basically the bindless handles. As you can see, I decided to skip the specular exponent, this guy, in order to simplify the implementation. I'll probably add that in the future, but for this example, this will be okay. Now, in your implementation, the material is probably very different. Everyone has their own way of defining a material, so just use this as a guideline, and then adapt it to your implementation. So now let's see the changes in the API. First of all, we have the init function. This used to take the vector of the basic mesh entry structure, and now we're also passing in the vector of materials, because of course we need to update all those SSBOs, right? And we have a new function to do that called prepare indirect render materials, which also takes this vector. That's it in terms of the declaration of the class, so let's see the implementation. So we start at the init function, which now takes the vector of materials from the core model and calls the new function prepare indirect render materials. But before we get here, we have the call to init meshes, which takes the vector of basic mesh entry and copies the material index into the new private attribute. As I've mentioned in the previous video, I prefer not to have pointers going between the two classes, so the information that we need, the transformation matrix, and now the material index, are simply copied into the private meshes vector. So now let's see how we prepare the materials. First of all, we resize the three vectors, colors, diffuse maps, and normal maps according to the number of materials, which is simply the size of the materials vector parameter. And now we traverse all the materials. We copy the three colors from this vector into the private member. We prepare a local variable called diffuse map bindless handle, which is set to the bindless handle of the diffuse map, if such a diffuse map actually exists. But if this is a null, then it will be -1, which becomes FFFF because this is an unsigned integer. And then this handle is set in the corresponding location in the diffuse map vector. We do the same thing with the normal maps, okay? Checking for null and then taking the bindless handle or -1 and setting it into the normal maps vector. The three vectors are now ready, so what we need to do is to load them into their corresponding SSBOs. So we create the handle of the SSBO by calling GL create buffers, and we upload the data using GL named buffer storage. Okay, this function takes the handle of the SSBO, the size of the vector, which is the size of the structure multiplied by the number of materials, and then the pointer to the start of the vector. So this is for the colors, and we do the same thing for the diffuse maps and the normal maps. All of this happens once when the object is initialized. In addition, we have some dynamic setup that happens in runtime before the object is rendered. Okay, let's remember the flow. The render function is called and takes the object matrix, which may change from frame to frame. Based on this matrix, we need to update the per object data SSBO. We bind the SSBO with the draw commands to the draw indirect buffer. We call GL multi-draw elements indirect, and then we disconnect the buffer from the binding point. In the function that updates the per object data, we calculate the world and normal matrices for each submesh. This vector is loaded into the per object data SSBO, and the vector contains this structure, which used to include a world matrix, a normal matrix, and now the material index. This structure has an exact replica inside the vertex shader, and notice that the material index which is of course a new attribute, is not a simple scalar integer. It is actually an IVEC4, okay, a vector of 4 integers. And the reason is that I ran into all sorts of alignment issues with the shader, because in C, C++, when you define a structure, the compiler may add all sorts of padding. And you can solve them by instructing the compiler to use a packed format here for this structure, but I found it easier to simply round this up to a vector of 4 integers and do the same in the vertex shader. But since we're using a single component in this vector, we only need to update the X component. Okay, the original material index, the one which is stored in the private attribute in the class and is only accessed on the CPU, this guy can be an integer, a scalar integer. But the structure which is shared between the CPU and the GPU has an IVEC4 here, so we only update the X. And then this component will be accessed in the vertex shader. So the other 3 are currently unused, but we can make use of them in the future if we need to. When this loop is completed, the per-object-data SSBO is updated as usual. We also bind it to its own special binding point, called SSBO index per object data. But now we also need to bind the 3 new SSBOs, right? The colors, diffuse, and normal maps. So I maintain a database of SSBO binding points, and in the previous video, I only used the first 2, one for the vertices, for vertex pooling, and the per object data, and now we have 3 new for the colors, diffuse, and normal maps. And we use them here before the render call. Okay, we need to bind each SSBO to the corresponding binding point, and it needs to match the vertex shader. This completes the changes to the indirect render class, so now we can take a look at the changes in the vertex shader. Okay, so the way this works is that the vertex shader needs to pass the material index to the fragment shader. So each vertex belongs to one of the submeshes, and this submesh has a material index, as we saw. So the vertex shader needs to pass that material index to the fragment shader. And then the fragment shader will use this index to access the correct textures, in terms of diffuse, normal maps, or whatever you have in your definition of a material. So we have an SSBO for that, called per-object SSBO, which contains an array of a per-object data structure, which is defined up here. And this is basically the GLSL counterpart of the same structure in C++. And remember, we've added a vector of 4 integers for the material index because of alignment issues. And on the GLSL side, we have the same thing. Okay, so this is an IVEC4. Now, in terms of the output attributes, we now have a new attribute for the material index. But notice a couple of things here. First of all, because this is an IVEC, we are using an integer here. And the reason that this is a single integer and not a vector like this guy is because we don't have the same alignment issues on the interface between the vertex and the fragment shaders. Okay, the alignment issues are only when we send stuff from C++ to the GLSL, but as you shall see later on, once we extract the X component which actually contains the material index, we can throw away this vector and send out a single integer. In addition, we're using the flat keyword here to specify that this variable goes as is without any interpolation. Okay, by default, output variables are interpolated by the rasterizer, but of course for the material index we want to get the original value, so we use flat here. Now let's go to the main function, and remember that we have this piece of code which handles indirect rendering. Okay, this is the original without indirect rendering, and this is for indirect rendering. So we need to update the output variable. So same as these guys, we access the SSBO per object SSBO using the GLDrawID, which basically tells us the index of the current submesh. We access the material index vector, and we extract the X component, put it into the output variable, and that's basically it in terms of the vertex shader. Now we need to see what the fragment shader does with this index. The fragment shader is also 4.6 core, and we have the same specification of the extension. The material index is now an input attribute, and remember that it has to be an integer, and no interpolation, so use the flat keyword. Same as the output from the vertex shader. Next we have the three SSBOs. The color SSBO contains an array of material color, which is this structure right here that contains the three colors. The diffuse and normal map SSBO contain a sampler 2D. Okay, so this is the same as the first example. Now this brings us back to the comment about using a single SSBO, because you may think, why not simply put the three arrays together in the same SSBO? Wouldn't it be simpler? So if you try that, you will get an error, and it turns out that there can only be one array of variable size per SSBO, and it has to be the bottommost variable in the block definition. And this is why we have to use three SSBOs, each with its own array of a variable size. If you know the size of the array up front, then you can specify it like that, and then add a single array of a variable size. In our case, the three SSBOs are of variable size, so we have to put each array in its own SSBO. Next, we have three functions to access the SSBOs. So the way that this used to work without indirect rendering and without bindless textures, of course, is that I would use a uniform variable called gMaterial of the material color type. Okay, remember, same as this guy. And then this material would be updated before issuing the draw call for the submesh. So of course, with indirect rendering, we can no longer do that. So I have a wrapper function to get each of the three colors. If indirect rendering is active, and that's the same uniform that we used in the vertex shader, we access the corresponding color from the colors SSBO using the material index. And when it's not active, we fall back to the original uniform. Now let's see where these functions are used. When we calculate lighting, in order to calculate the ambient color, we multiply the color of the light source by its ambient intensity, and then by the material ambient color. So instead of accessing that uniform directly, we do that using the wrapper. Okay, so this is for ambient color, this is for diffuse color, and of course for specular. So I don't know if this is the most performant way to do this, and you may create a specialized version of this function for direct and indirect rendering, but I like using the wrapper because at least it keeps the code clean. So this is for the colors, and we have the same thing for the diffuse and normal map. As you can see, when we calculate bump or normal mapping, we have to sample the normal vector from the normal map. And this guy is a simple sampler 2D uniform. And now if indirect rendering is active, we go to the normal maps SSBO using the material index, and this is now the sampler 2D object that we sample from. This is for normal mapping, and exactly the same thing for diffuse maps. I wasn't very consistent in terms of naming here, but anyway, this guy also holds the diffuse map. And that's it. Now let's try to run the demo. And here's the jumping character with the textures working correctly. And that's it for today. So thank you for watching, and I will see you next time.